So good morning students. So welcome back to the digital signal processing class. In today's class we are going to discuss the concept of the IIR filter, that is nothing but infinite impulse response filter. So in the today's class we are going for unit 2. In that we will be having IIR filter. So what is this IIR is all about? So what is IIR stands for? It is nothing but infinite impulse response. So what is this IIR? What is the meaning of infinite? Infinite means there should not having a particular limit. It is infinity. Till infinity the impulse response. Impulse, whatever the impulse value h of n is called it as impulse sequence. So what we are saying, whatever the filtering we are learning in the unit 2, that is nothing but infinite impulse response. So what is the type of it? How do we define this thing? We can say that infinite impulse response filters are recursive type. Recursive means keep on coming one after the another. That is recursion. Recursion is there possible for IIR filtering. So this is what type of filter it is. Infinite impulse response filters are recursive type filters, and it is used for present output that depends upon the past input as well as the present inputs. For both the inputs it is depends, and it is also one of the type of filters which we can define for sample value, in the sense if you do have a sequence. So what is the sequence? If you do have, suppose you had the sequence like this, so it depends upon the present input. Suppose this present input is x of n and previous input is x of n minus 1. This is previous input. It depends upon the sample values, whatever the samples we do have, n number of samples if you are taking. For n samples, output is y of n, output samples, and this sample functions. So whatever the samples values we are going to take, that particular values it can going to be taken. That means IIR filters not only decide the factors for which it is going to get the particular form of it by using the filters. What are the filters? We know it. We know about low pass filter, high pass, band stop filter, band pass filter. So band stop is one of the thing which we are going to use it, and one more name for that is band rejection filters. So by using these all 4 types of filters, we are using infinite impulse response to find out their particular output. So for that what we are doing, we are applying this IIR filtering. In that, first thing what we need to keep in your mind, IIR filter is what? Recursive. So the output of that particular depends upon present input and the past input, both the values. So in that one, what are the things we need to keep in the mind? We need to keep in your mind that whatever the bounded input it has 2 kind of factors. One is stability factor, and the second would be the transfer function of that particular factor. So when we want to find the stability factor, it should be get a output response. That means whatever the functions we need to write, suppose if I am saying h of n, that should be less than infinity. Mod of h of n should be less than infinity. That means it should be a function of realizable. Means whatever the filter we use, this filter should be realizable, and it should be stable. That means we need to get the response of it. We need to get the output of that particular response. If you are getting that response, that means it is what? Realizable. If you want to get the stability, how do we define? Stability factor of any functions you have seen in signal and system. So in that what we have seen, the bounded input should produce the bounded output, and it depends upon the present inputs as well as in past inputs. So based upon that 2 parameters, we are saying that should be used for that particular filter. And one more condition, h of n should be 0 for all values of n. So for all values of n, that should be what? H of n should be 0 for n less than or equals to 0. If this condition satisfies, then we can say that the IIR filter can be realizable and stable based upon the functions. So based upon these functions, we can say that particular point. Next thing, we need to get the transfer function. What is the meaning of transfer function? So if you do have the input as, suppose if I am giving input of x of n, I am getting the output as y of n. If I want to find out output by input response, that means transfer function. What is the meaning of transfer function? If I am giving any particular values to the response, like if I am giving the sine wave, cos wave, tan wave, whatever the waves if I am giving, based upon it, if I want to find the output response y of n divided by x of n, then it is called as the transfer function for that particular filters. So I need to find out the transfer function. So for that, we need to apply the Z transform for these functions. So what is the Z transform is all about? It states that if you had Z transform of x of n, if you want to find Z transform of x of n, summation n is equals to minus infinity to infinity z power minus n x of n, right? This we know it by using Z transforms. So in this, it is bonded inputs produces bonded output. So BIBO operation. Bonded inputs produces bonded output. For that, we are writing what actually? We are finding the transfer function for our IIR filter. In that, how do we find this thing? We need to write first its what? Output response, and then we need to divide by that particular factor with input response. If you are doing both of them, then you can able to find out IIR filter complete transfer function of it. So how do we find? We need to write the function. So we wrote y of n by x of n. So how do we write y of n value? Suppose I am defining two coefficients. One coefficient is ak, that defines input. So what I am writing for this, if I am mentioning here, is having some coefficient of input is ak and the coefficient of output is bk. So I am applying the Z transform for it. So how do we write this particular thing? I can write y of n by x of n summation. What I am writing? I am writing the transfer function. So how do we write the transfer function? H of n. What is this value? N is equals to, suppose I am taking one bonded, h of n z power minus n is equals to same factor summation ak z power minus k is equals to 0 to infinity by 1 plus summation k is equals to 0 to infinity bk z power minus k. So this is your transfer function of IIR filter. So this is the way you can find the transfer function. So this is what upper factor is, what is about output. So output factors we are using here, input is bk and the output is ak. So ak is the output factor and we are applying what? We are applying Z transform of it. So we got ak coefficient into z power minus k because the limits are starting from k. So whatever the limits are, that's starting from 0 to k, that is nothing but one-sided. It is not two-sided, it is one-sided. We put the value divided by the input factor. So if you are dividing this way, then you find the transfer function of your infinite impulse response. So next thing we'll see what are the types of filtering it can consist of. Since it is what frequency domain part, so it also has the same low pass filter, high pass, band stop and band pass. In that also we are using this part. Let us see that one. So next thing we are writing the filters of it. What are the frequency selective response of it? We want to find for IIR filters. Let us see that one. So suppose we are going for frequency selection. How do they select the frequency? Frequency selective filters. So in that, what is the meaning of frequency selection? It should have some certain band of frequency, the bandwidth of that one. In that, we'll go for two types of frequency. One is what? Upper frequency, lower frequency, and the critical frequency. What is the critical frequency? A point in which it should segregate into two parts. One should be the stop band, another should be the pass band. So in that, if I am using the filtering means they should allow the certain band of frequency in the response and they should reject the remaining band of frequency. When it is allowing the certain band of frequency, then it is called it as pass band. If they are rejecting the certain band of frequency, then it is called it as stop band. So we do have these two types of band, pass band and stop band. In that, if I am using a low pass filter, if I am using a filter in which, if I am using low pass filter, in this what is the value? It should allow lower frequency and it should reject higher frequency. That means like this. If I do have the frequency response of your transfer function h of omega, suppose I am telling the omega angular frequency h of omega with mod. This if I want to find out, how do we get? This is my pass band, this is my stop band, this is what actually, this is the critical frequency omega c. So omega is equals to omega c, it is their value, and omega is less than omega c. Omega is greater than omega c. So we do have three ranges. Omega is less than omega c is what? What is that? It is pass band. That means it is allowing the frequency. Allowing that components of that frequency. Omega is equals to omega c is nothing but again is come under the same point, pass band only. But it is a boundary, a barrier in which the pass band and stop band has been segregated. So this is the same thing. Next thing, this is what stop band. That means it should attenuate or it should stop it or it should reject it. So that is what stop band. So when omega is greater than omega c, it is going to stop it. Stop that particular band of frequency. That is nothing but you will be having the concept of low pass. So this is what ideal. If you want to get the practical of it, how do we write? We'll write like this. We'll mention this way. So we'll go for finding the RMS value. So that is nothing but 1 by root 2. 1 by root 2 is 0.707. This is your critical frequency. In which what is the type of band it is? It is nothing but pass band till here. This is what critical frequency omega c. Pass band is till here. This is all whole about stop band, right? So what is the value of this one? Suppose this is your having the gain 1, having omega here. So this particular band of frequency, if you want to find out, then come under the pass band and remaining is in stop band. So you will not get the ideal. Ideal is what? 100% efficient. In practical, if you want to find low pass filter, you will not get the 100% efficiency. To get that one, to achieve this thing, we'll go for RMS values. That is nothing but root 2. We'll divide by root 2. That is 1 by root 2 is nothing but 0.707. Based upon that, we will find the response of practical low pass filter. So like that, we can design for high pass. High pass is quite reverse of it. In that, what we'll get? Like this. After critical frequency omega c, it will allow the components. This here, before the critical frequency, it allow here. Here, after critical frequency to allow, before that it is having the stop band, and here is the pass band omega, and it is impulse response. So h of omega, h of j omega, you can write here. You can get with imaginary component also. We mentioned h of j omega with mod. Nothing but we are finding the magnitude of it. So how do we mention this thing? Omega is less than omega c. That shows that it is in which band? Stop band. See, before it, do we had what type of it? Less than. Less than means before this thing it is in stop band. It won't allow any frequency component. Omega is greater than omega c, or omega is greater than or equals to omega c. It is in which band? Pass band. That means after that it allow the frequency component till infinity. Depend upon till what frequency you applied, till that it will allow. So this is an example of what type of filter we are dealing with. We are dealing with high pass filter. Second type of it. This is the first type of it. Similarly, if I want to get with practical value, this is what ideal. If I want to find practical, how do we get? For stop band here is there and the pass band here is there. So it will stop until unless we reach with critical frequency. After the critical frequency, start giving the output signal like this. So this is what gain. Suppose let us assuming this is having a gain 1. So h of j omega with mod. So before 1, if I am dividing with RMS value, so what I'll get? I'll get 0.707. Here omega we are plotting with h of j omega. So this is what in which band it is right now? It is in high pass filter, pass band. This is the stop band. So this is the range. How do we write the range for high pass filter? So this is the way we design low pass ideal high pass filter and practical high pass filter for both the low pass ideal and low pass filter of practical. So this is the low pass both those things, and high pass both the practical and the ideal. That is nothing but theoretical. So both the things we have seen. So next type of filters we do left with band pass filter and band stop filter. That one we'll see now. So next part we are going to third type of filter, that is nothing but band pass filter. So next, third one is band pass filter. That means we should allow the band of frequencies to pass it. That means whatever the frequency components we are putting, that band of frequency only it will allow, remaining it should reject. That means I'm using the filter like this. I'm putting, this is the band, having some lower frequency omega L and having upper frequency omega, and having critical frequency omega C. This has become stop band and stop band. This has become now pass band. That means it's allow this particular band only between omega 1 lower, omega 2 and higher, and remaining it should reject. How do we write the values of omega? This is what magnitude of h of j omega, having the gain ideal value is 1, right? So how do we write the range for this? To write the range, what will write? 0 to, what is the value? 0 to omega L or omega 1. It is in stop band. Again from omega 2, omega 1 to omega 2. It is in which band? Pass band. Then omega 2 to infinity. It is in which band? Again it is in stop band. So what is the conclusion of this? It has 2 stop band and 1 pass band. This much band only it will allow. After that one it will reject. So this type of filter is what is that name of that one? It is nothing but band pass filter. So what is the ideal response? How do we write this thing? So for ideal we'll write 1 stop band. It has some lobes, fluctuation lobes we'll mention, and it has stop band. So this is what gain is 1. Suppose having here omega 1, here is omega 2. Between this we have to have critical frequency omega C. We are plotting the graph between omega to h of j omega with magnitude. This is what? 0.707. Clear? So this is the way we will represent band pass filter. Likewise we can go with next part, that is nothing but band stop filter or band reject filter. Band reject filter. Reject means it is a quite reverse of this. It will reject this much band, it will allow the remaining band. That means the same filter will mention with omega on x-axis and impulse response. Impulse is h of j omega of magnitude. So here we'll mention this is the band and another band. It is allowing, that means pass band here, pass band here. In between what should be there? Stop band. So here what is the value here? Omega 1, omega 2. So omega 1, omega 2 it has, and this is the value for it to represent, right? So how do we mention the condition for it? So for writing the condition, what I can write for this one? I'll mention omega 0 to omega 1, it is in pass band. So 0 to omega 1, it is in which band? It is in pass band. It allows that particular frequency component. Similarly, between omega 1 to omega 2, it is in which band? Stop band. After omega 2 to infinity, it is in which band? It is again in pass band. So quite reverse of that one would be this one, band reject filter or band stop filter. So this is the way we'll write it down. So how do we write ideal value for it? Ideal, we got it. We need to write its practicals. How do we mention the practical for this? I can mention in this way. What I'll write? I'll draw it, the response of it. That means it should what? Allow the frequency component. So what is that? It will allow means like this higher frequency, then it will reject it. So this is the band of frequency it will reject, again it will allow. Omega with h of j omega with magnitude. Having practical gain is, ideal gain is 1, practical will take it from 0.707 RMS value. So we got this one, omega 1. If you go for the same condition, this is your omega 2. So it is allowing the frequency component. So this is a frequency component allow. This frequency components also it will allow. And this is your frequency component, it will allow. Right? This is the way you do have the band stop filters. So these 4 types of filters will mostly use in our IIR. IIR, that is nothing but impulse the frequency response filters we are using. In that one, infinite impulse response, if you want to find out, in that one we are using these 4 types of filters, and we want to solve the problems related to Butterworth approximation. There is a technique to find the transfer functions. That is nothing but n domain sequence into k domain sequence. We'll be having, how do we have find like butterfly? We have taken the steps. After that, by using the steps, we have used it. We have find the particular functions. In the same way, by using in Butterworth approximation techniques, we can also find out the transfer function by using these all 4 types of filters. So there are 2 concepts in it: analog filters, digital filters for Butterworth approximation, for Chebyshev approximation, analog filters and digital filters. So these are 4 types of filters. By using these all 4 combinations, we are going to deal in detail in unit 2. So that complete part and the working of it we will see after this complete explanation. Just make a note of it and practice this all type of 4 filters. So as you can see in this, what we have given, we have put the ideal values and practical values for both band pass and band stop. So draw it and practice it in detail wise. We will see in the next class. So thank you for today's class.